Hello, hopefully you can hear me all okay now. Apologies for that. The whole thing sort of went down again for a second. Once again, we'll be going in just a moment, and we should be able to log in now and be able to see all of your questions. So just need to refresh. Uh, Refresh and start. Uh, Refresh your browser. Okay, there we go, and we should be good. Hopefully you can hear me. Do say hello if you can hear me, and then we can get going. Okay, just give everyone a couple of moments. Can you hear me? Maybe not, because it sounds like my microphone's not working. Okay, hello, can you hear me? Can you hear me now? I think you might be able to hear me now. Super, brilliant. We'll get going now then. Apologies for that. Like I say, I've just had to switch computers and a heap of other things, but I think we might be. Is it still echo? Okay, good. Right. All right. So let's have a look once again. A bit later than start, hoping they're 25 minutes. Good, good. So we're looking at equilibrium moles. And what we need to do is we need to find out the change in moles. So for this hydrogen sample here, the hydrogen, to get to equilibrium moles, we've got to do 10 minus in order to get to the equilibrium moles of 3. Therefore, for the iodine in this case, this is going to be, so here we've got a 1-to-1 ratio. It's also going to be -7. We get an equilibrium moles here of 3. On the right-hand side, we've got a product. So in this case, we're not going to get a decrease, but we're going to get an increase in moles. And it's going to be more than simply just 7, because here we've got a 2-to-1 ratio. Okay. Therefore, the change in moles is actually going to be 2 times 7. So our equilibrium moles in this instance is actually going to be 14. Okay. Let's have a look at another example here. Here we've got, again, some initial moles. So what we have to do is we've got to work out what the change is and then see how that affects our equilibrium. So in this case, we've got methanol and chlorine, and we've got this SO2Cl2. That doesn't make much of a sense, to be quite honest with you. So I think that must be more like something like that. Don't worry about it too much. You could just describe it as A, B's, and C's. Interested, importantly, on the product side, we've got a change of plus O. We've got a 1-to-1 ratio. So again, we must be plus 0.4 here, and we've got 0, so it's 0.4. And this side, we're going down because we're reactants. We've got to take away 0.4. So our equilibrium moles is going to be 1.6. Okay. So what we're going to do is we're going to move on and we're going to see how we can calculate Kc calculations. Okay, it sounds like we've got some issues here. I'm just going to check the live control room. Do just drop me a line if you're having issues. Okay, thanks. Do just update me, please, if you tell me it's gone, because otherwise I think it's gone again. Okay, so we'll have a look at some of these Kc calculations. Kc, if we got an equilibrium constant, we're going to move on to rates of reaction, is for an imaginary reaction here, if we've got A plus B going to make C plus D. So this is our imaginary reaction that we're looking at. Our Kc is going to be equal to the concentration of the products here, and these are then raised to the power of the stoichiometry, so that's the number in front, over the reactants raised again to the power of their stoichiometry. So we're going to use this here to try and work out some values of Kc. So we've got an example, and we've chosen this one specifically because we've got a ethyl ethanoate and water. So here again, this is an example of an organic reaction here, which is the paper that we're interested in. It's 200 grams of ethyl ethanoate and 7 grams of water. will reflux together at equilibrium. The mixture contained 0.25 mole of ethanoic acid. Calculate Kc for the hydrolysis of ethyl ethanoate. So what we found out, well, what the first thing to do is to work out the moles at the start. So we've got 200 grams of ethyl ethanoate. So you're going to need at some point here a calculator in order to work out the MR. So the moles here is going to be the mass divided by the MR, where the MR here is going to be 4 times by 12. Plus we got 8 hydrogens, and we've got 2 oxygens. So we're 200 over 88, giving us a starting moles of the ethyl ethanoate of 25 over 11, or 2.272 moles at the start. I'll put another 7 in there. And the moles of water here, that was over 88. The moles of water is going to be 7 over 18, because we've got 7 grams divided by the MR of water being 18. And here we've got 9 moles of water. We're starting off with none of the acid and no ethanol. What we're told is that the equilibrium mixture has 0.25 moles of ethanoic acid. So we've got 0.250 moles. So what that certainly means is that's gone up by 0.25. And our moles of propanol here, so we've got ethanoic acid gone up by plus 0.25. We started with 0 amount of ethanol, so this is now gone up to 0.25. Shouldn't we round the answer? No, because these aren't answers yet. Okay, these are just working, so we don't want to round the answer too soon, otherwise we'll end up with errors. So here is our change in moles. Here is our start moles. And what we need to be... No, not when working out the moles. Just make sure you're... Don't round too early. Wait till the end. You're going to have 0.25, and then here, because these are reactants, these are going to go down by 0.25 and down by 0.25. So we end up here 2.2727 minus 0.25, giving us 2.5. I'm going to change the pen here. And 0.389 minus 0.225, giving us 0.139. So these are equilibrium moles. Now this is quite important. I'm just going to remove my mole calculations here. Kc is the products here of the reaction. So we got ethanoic acid and we got ethanol. Notice that there is no stoichiometry because these are both 1 in this example. Yes, you're right. Good spot. So that's about 2.02 in fact, isn't it? Kc here, good spot. Thank you, Arwen. Is get over the C2, CH3, and then the water. Now, in this example, notice that the stoichiometries are all constant and they're all the same. Therefore, there's no need for a volume, and this can be simplified to just simply the moles. So in this reaction here, we can simply go to the 0.25 times 0.25 over 2 times 0.139, and we don't need to use the volume. We throw that into our calculators. I've rounded a bit early here on the 2, but it will work for our example here. Then we end up with an answer around about Kc here of about 0.225. And then in this particular instance, we've got the value of Kc, or the units even, are unitless. The units for Kc vary, and you've got to be able to work those out. I'll show you those in the next one. Okay. Key points about Kc is constant for value or for different pressures or concentrations. And really we're talking about concentrations with Kc, but when you look at Kp as well, it's constant, but Kc changes with temperature. And it will change with temperature, as we've discussed before, depending on whether or not the forward or backward reaction is exothermic or not. So remember what we've said before is that here Kc really is simply a ratio of the product's concentration over the reactant concentration. Therefore, if we've got a reaction here where we've got reactants and products, if the forward reaction is exothermic and we increase the temperature, if we increase the temperature here, what will happen is we will increase the amount of reactants as we shift the equilibrium, and therefore, for that particular example, we would decrease Kc. However, if we had a reactants and products scenario here, where the forward reaction was endothermic, and we increase the temperature, and we would decrease the amount of reactants, we would increase the amount of products, and therefore Kc would increase. So the value of Kc changing with temperature will depend upon whether the forward or backward reaction is endo or exothermic. All right, Kc here is always constant. I'm not going to work through this particular question. They all work in exactly the same way. So do make sure that you're happy with working out the change, the start moles, the change, and then the equilibrium moles for all of your questions. As I say, there's heaps of past paper questions on the site there. If you have a go at some of those and feel that you're stuck in any way, drop me a line and we'll happily spend a bit of time working on Kc calculations next time. Any questions so far? I'm just going to pause for a drink. Okay, so let's have a look at. Okay, so on part C here, so what effect would increasing the temperature have on the equilibrium position and Kc? So here we're given information that the enthalpy change is greater than C, and the equilibrium will be affected by temperature. In this particular example, I'll do this bit in blue. If I increase the temperature, the reaction is going to go in the forward direction because this is importantly endothermic because we've got a positive value. Therefore, we're going to increase the temperature, reaction will go in the forward direction. Therefore, increase the concentration of the products and will increase the value of the Kc. J, the mark schemes for the past paper questions I will put in the past webinar section straight after this session. Okay. So, any more questions on Kc at this point? All right. We'll therefore move on to start having a look at the more detailed rates of reaction section for the organic paper too. Now, as a quick reminder, we'll go through the kinetics, the collision theory, Maxwell-Boltzmann distribution. I don't want to spend very long on this because I want to get at looking at how we do the questions later on. So collision theory, we have to be able to recall collision theory, and it's simply the idea that in order for a reaction to occur, particles must collide. So we've got to have a collision, and they must collide with an energy greater than the activation energy for the given reaction in order for that to occur. Now, there's different ways that you can do that. Remember, hopefully from GCSE, you can increase the pressure, you're going to get more collisions. You can increase the temperature, or you can add a catalyst. So they're the sort of things we need to be able to recall. Increase the pressure, we're going to have more particles will collide because there's more particles in a given space. Increase the temperature, well, there's going to be more particles with an energy greater than the activation energy. And then add a catalyst, you're going to reduce the activation energy, or in essence, rather than reduce it, you're going to offer an alternative pathway with a lower activation energy. And therefore, more particles have an energy greater than the activation energy. Okay, so surface area as well. So you could increase the surface area. There's going to be a greater chance. Increase surface area, increase the chance of collisions. Good. Thank you very much. Okay. Now, that idea really is some of your GCSE terminology. The new thing that you've got to be aware of from the AS course. So again, Here we've got a diagram here, which we call the Maxwell-Boltzmann distribution. I'm just going to draw it out below here. Importantly, we've got the number of particles, and the area under the curve is equal to the total number of particles. And then we've got some possible scenarios. So we're just going to simply sketch the curve that we've got above, that we've got like that. Importantly, this line here does not retouch the x-axis. Okay, so it always stays high. Never draw it. Doesn't matter really how high it is, but make sure it's always above it. You can then describe different scenarios. If we increase the temperature, then what we're going to have, and we've got energy along the bottom, we're going to have more particles with a greater energy. If we increase the temperature, keep the same number of particles, so the curve shifts right and looks like that. So this would be a greater temperature, and we got more particles with a higher energy. Under the curve is still the same. The other option we need to be aware of here is if we've got a colder temperature, then our curve shifts left, and this would be a lower temperature. It's got a higher peak because we've got more particles with a lower T. The activation energy in each of these examples is going to remain constant. So this might be the activation energy. And we can see at the higher temperature here, we've got significantly more particles with an energy greater than the activation energy. If we use a catalyst, then we would lower that activation energy, and we would shift perhaps to here. This would be the activation energy with a catalyst. And again, we increase the number of collisions because we've got more particles with an energy greater than the activation energy. The only other thing sometimes you're asked to do is if you've got a higher pressure, so you've got more number of particles, the curve would remain the same, but everything would be shifted higher, so there'd be a greater area under the curve. That should hopefully refresh our memory of the from the AS course, and we're now going to move to the rates of reaction where we have to quantifiably look at how the reaction changes. I'll just pause for a second and see if you've got any questions about rates of reaction from the year 12 course. Okay. Slightly more complicated situations here, where we're going to look at the rates of reaction where we're trying to measure it quantifiably. Measure units here, so the rate is described as either the loss of products or the concentration of products formed over time, or say the reactants used over time. Therefore, the rate has always got a value of seconds to the -1 in it, because we divide seconds to the -1, and it's also a concentration per second. The other thing to note is that the rate will change quite often with time. See that change because we've got a curve for this experiment. Let's have a look at how we measure then the rate of reaction. Here we've got some data. We've got the concentration of a sample, and we're measuring it as a function of time in seconds. And because this is going down, this is certainly going to be the reactant. In order to do this, we have to measure the gradient, and the gradient to a graph is the change in y divided by the change in x. So to measure the gradient for a curve, we have to Hello. Cool. So you should be able to hear me. And apologies, it's the internet connection this evening is being a little bit slack on me. We should now be able to observe the gradient change. Have you got any questions here about measuring the gradient? Sure. Okay. So the rate is a measure, is taken as the concentration over the time. Okay. And the concentration divided by the time we can calculate from the gradient of a concentration time graph. We measure the gradient by taking tangents. I'm going to draw these tangents here in green. So we've got tangents at two different times. Our first tangent here is the change in y, which is 0.5 over 26, and gives us a value of 0.019 dm cubed seconds to the -1. And our second tangent we can measure again for a reaction. Here we draw a tangent to a curve, and that gives us 0.28 over 58 which is 0.0048 mole GM minus 3 seconds minus 1. You'll notice importantly here that the rate is changing during the course of the experiment, and the rate changes as we change the concentration of the reactants. JK, are you happy with that discussion so far? Cool. Okay. So here's a typical sort of thing we might expect to do. Now, a description of the order of the reaction is something that we'll come on to in just a minute. All we're actually looking at in this section is the rate of a reaction and check that we can measure the gradient. We'll look at orders in just a moment, and this is key. So importantly, the rate of reaction is something that will change with time. Move on to orders, and importantly here that we're talking about orders, that as we said, the rate here, something that can change, and it's going to be proportional to potentially our reactants. In other words, a concentration of the reactant somehow. And the power of the proportionality here is going to determine whether we're zero or first or second order. But this must be measured experimentally. It's not something that we can just work out by looking at the overall equation. We can work it out by looking at the stepwise mechanism. The other thing is that the overall order of a reaction is equal to the individual or the summation of the orders of the reactants. In other words, if I was two first order reactions with respect to A and with respect to B, overall it would be second order. Okay. Let's have a quick look at seeing what effect order would have, and then we will go and have a look at how we work them out using something called the initial rates method. So we have in these experiments, the rate is equal to the rate constant, and we'll talk about that in a little while. And in this example, compared to the concentration of G and the concentration of H. Now, because there's no number here, what we're describing here is G and H are both first order. In other words, the rate is proportional, directly proportional to G. So whatever I do to G will also happen to the rate. And here the rate is also it's back again. So the rate is proportional to G and proportional to H, and they are both first order. So in this example here, we got the initial concentration of G. We're starting off with 0.2. We've starting off with 0.1 for H, and the initial rate was 0.4. So in this reaction, we've decreased the concentration of H by 2. So that would have an expected effect on the rate to decrease it by 2. So the initial concentration of G is actually the same. In our next example, let's have a look. Just trying to zoom in a bit. Experiment 3 here. We're seeing that the initial rate is gone from, if I compare experiment 2 to experiment 3, well, the difference in concentration between H is it's gone up by 4. So that would mean the rate should also increase by 4. So it should go to 0.8. However, the actual rate is 0.4. Therefore, the concentration of G must be pulling that down, and therefore concentration must have decreased by half. So this has gone up by 4, and this has come down by 2 in order to fulfill those rates. Let's have a look at number 4 here. In compare 3 and 4, I've decreased the concentration of G by 2, and I've increased the concentration of H by 5. So the rate J, you're absolutely right. Yeah, I'll do one more. I'll show you how you could do the rates. You're absolutely right. You could calculate K there and then work out what the expected rates would be. What that also provides you is a test of checking it out, that your answer is correct. I'll do the final example here. Well, not the final one, but do number 4, and then we'll move on to the next example. So number 4, we've decreased. G has gone down by 2, while H has gone up by 5. So overall, the rate will have increased by 2.5. So here, the rate is going to be 0.4 times by 2.5, giving us a value of 1.00. You're absolutely right, though. If you wanted to work out the value of K, you could have sat there and calculated K and then plugged in your values. Okay. Have we got any questions about how order affects the rate here? Could I calculate H? Where? Sorry, Kay, I'm not quite sure where you want me to calculate H. Number 6, sure. Okay, number 6. Let's have a look at number 6. All right, so number 6, if I go from number 1 to number 6, this is increased. So number 1 to number 6, G increases by 8. So we'd expect the rate to increase by 8. And then let's have a look and see what happens to the actual rate. The rate actually increases only by 4. Therefore, the concentration of H must have gone down by 2. So the value here of H is going to be 0.5 divided by 2, which is 0.05. And in fact, I think it might be worth... Cool. Okay. We could also work out the units of K for this particular example. I'm just going to go over to the side, make sure we're happy with the units. So rates is equal to K G and H. So our rate is moles, dm minus 3 seconds minus 1. That is always constant. We've got K, we've got moles, dm minus 3 for the one concentration, and we've got moles, dm minus 3 for a second concentration, which means our units of K here become moles dm minus 3 seconds minus 1 divided by moles dm minus 3 divided by moles dm minus 3. These cancel, so K in this example is moles minus 1 dm cubed seconds minus 1. Notice that the units for K vary depending on the overall order of the reaction. The overall order of this reaction, these are both first order, and therefore this is second order overall. Okay. I'll have a quick look at 14 going on to 15 here. Okay, no, the units of K are not the same as the units of rate. So the units for K depend on the units of rate. So depend on the overall rate. The units of rate are constant, and they are moles dm minus 3 seconds minus 1. If you've got a first order reaction overall, then we would have moles dm minus 3 seconds minus 1, moles dm minus 3 due to the concentration. The units of K here would simply be seconds minus 1. We just saw with a second order reaction, our unit for K would be moles minus 1 dm cubed seconds minus 1. If we had a second order reaction, a third order reaction, let's imagine we got A, B to the 2, well, we would still have moles dm minus 3 for the rate, seconds minus 1. We would have overall moles cubed dm minus 9, and our value for K then would have to be moles minus 2 dm 6 seconds minus 1. So be aware that our K here, the units will change. I hope that answers your question, Jay. All right. We're now going to look at two ways here of identifying the rate of reaction and the order of the rates of reaction. So you need to be aware of both of these methods. The first is the initial rates method, and this is a practical method of which is described in the key practical skills. So make sure you're aware of this. The second is to use a method whereby you measure the gradients of graphs at different times. We'll go through the initial rates method. We'll have a couple of examples. Then we'll have a look at the gradient method, which is much easier in fairness. We'll go and have a quick look at then the Arrhenius equation after that. Okay. Initial rates method, what this requires us to do is to take the initial rate and then what you're going to do is change one thing, one concentration of reactant at a time, measure the initial rate, then you'll repeat this, changing the concentration and measure changes to the rate. And what you end up with is data that looks very much like this that we got on the table. Again, the computer doesn't seem to want to let me to zoom in on anything today. That's a bit better. Hopefully you can see that. And it's just also zooming to the same point. Okay, let me just check. Can you still hear me? I'm not sure if I lost connection then. Hello, can you still hear me? Yes, good. Okay, brilliant. Okay, so let's have a look at the initial rates method and see if we can work out what's going on. So let's have a look. We'll do A. I might have to do it down the bottom because it won't let me zoom in today. We've got to compare two experiments to find out what's going on. So we look at experiment 19 up here, and we're going to compare that to experiment 20. Thanks, Anon5573. Yeah, you should be able to observe by clicking on 720 HDP to be able to see it. Apologies, I can't actually make that bigger this evening. Like I say, I've had a slight malfunction on computers and I'm using a spare one from work here this evening. But I didn't want to let you down. We'll compare experiment 19 to experiment 20. Well, what's occurring here is A is remaining the same, and we double the concentration of B, and doubling the concentration of B increases the rate by 4. In other words, it's increased the rate by 2 to the power of 2, and therefore we can say that this is a second order reaction with respect to B. Then the next thing to do is to try and compare something else. So this time we're going to compare experiment 19 and experiment 20 we'll go for, and 21. In this, we're choosing this one because, well, B is remaining constant, but we're doubling the concentration of A. Doubling the concentration of A doubles the rate. Therefore, we can say we're first order with respect to A. And what this means is we get a rate equation where we've got A is first order, we don't need a number here, and B is second order. The total order for this reaction then, we can say, is third order overall, because we add 1 and 2 together. Okay, we'll do another example here. We'll have a go this time at B, and I'll just see if I can take a screen clipping of B. Oh, no, it's not going to let me do that, is it? There we go, it will let me do that one. Great. So we can see that. There we go. I think we might have got around one of them. So this time what we're going to do is we can compare, again, choose two experiments, ideally where one doesn't change. So here, 22 and 23. Concentration of E remains constant. So here in concentration of D doubles. Here the rate remains unchanged. And if there's no change when we increase the concentration of something, then we're zero order with respect to D, which makes our lives a lot easier because it doesn't make any difference what we do to our value of D, whether we increase it by 2 or whether we increase it by 4. It should have no effect whatsoever. Now let's compare 23 and 24 then. Well, D has no effect because it's zero order. So all we have to look at here is then we're going to say we're increasing the concentration of E by 4, and the rate here, and if we're not sure what the rate's increasing by, we can simply divide one by the other. 0.2 over 0.8 over 0.2 is giving us a value of 4 again. So this one is increasing by 4. So we're first order with respect to E. What that gives us overall is a rate equation here where we K. Now I can put in D, but remember that's a value of 0, and E. So actually that one cancels out, and our rate equation is simply K to the multiplied by E. Okay. I think we're still live. Have we got any more questions here on the initial rates method? Yeah, I can have a go. See, of course. Right, I'll try and make that nice and big again. Cool. So C is now getting a bit more confusing here, isn't it? Because we've now got real numbers in, which we can expect to get in the exam. Okay, here we go. Question C then. Whoop. Here we are. Ooh. P reacts with Q to form various products. And we got some rate information. We've got some funny numbers here. So I'm just going to grab hold of my calculator. So in all of these things, what you need to do is to look for a reaction where we observe a change and where something remains constant. So this one, I'm going to this one. So I'm going to compare 25 and 26. So Q remains constant. The concentration of P, though, increases by 2. And the question is, what happens to the initial rate? Well, if I'm not too sure, I can do 0.004 divided by 0.002. So that has also increased by 2. So the rate with respect to P is first order. Now, what I'd suggest is if you're doing these, divide one by the other, you've got 2 options. If the increase, there is no change, then it's going to be 0 order. If the increase is the same, then it's going to be first order. And if it's different to either being no change or being the same change, then it must be second order. So you don't always have to work out these. You can just work on that function. Now let's have a look at some of the others. Well, okay, we've got to look at one of these changes, and well, it's probably easiest here to compare these two, because it's probably easier to say I'm going to double something rather than increase it by 50%. So I'm going to compare 26 and 28. And in doing so here, I've increased P by 2. So I've increased P by 2. I would expect the rate to be doubled. So increase the rate to 0.004 times 2. So I'd expect the rate to be 0.008. What I have done here is I've increased the concentration of Q by 2. So this, well, what effect does this have on the rate? And let's have a look. If I now do 0.01598, which is pretty much 0.016, divided by the expected rate, which is 0.008, that's going to be 2. And therefore, here I've increased by Q by 2, the rate's increased by 2. So we are first order with respect to Q. And so our rate is P, Q, and the overall order is second order. Owen, did that help? Jay, cool. I'm really pleased you asked that question, Jay. What about on a graph? This is the first method with which we have to do our understanding the orders of reaction. We're now going to go and look at the second method, which is looking on a graph. All right. So, like I said, initial rates method is the first method that you need to know about. The second method is indeed looking at a graph. And what we have here is for any reaction, if we measure the concentration of X as a function of time, much like we've seen before. And then if you take gradients, so if you then measure the rate at different times. Now, in order to measure the rate at different times, what you'll have to do is you will have to take tangents and measure the gradient at lots of different intervals. So like we saw at the beginning. So in order to get these graphs, well, you'd measure the tangent. Obviously for the 0 order one, it's a straight line, and therefore the rate remains unchanged. So you measure the rate at different times, and then you plot the rate versus the concentration of the reactant, and then you will get some plots like this. You will either get one that looks like here, and what this one says is as you change the concentration with over the course of the reaction, the rate remains unchanged, and therefore this is 0 order. All right. Now the first order reaction, in order to measure the rate, we would have to take lots of tangents. So you'd have to do like we saw earlier, and then measure the gradient. You would then be able to plot the rate as a function of the concentration of X. And here this is directly proportional. And therefore we can say that this is first order. In other words, the rate is proportional to X to the power of 1. And then the final graph that we would draw here, well, we've got the concentration again of the reactants with time. Once again, you do your tangents along the line, and you then plot your rate versus the concentration of X. And this time we've no longer got any straight line, but it changes to the power of 2. But again, it doesn't matter whether you know that's a power of 2 graph. The important thing is it's not a straight line, and it's not a linear line. It's not a constant line for 0 order, and this is second order. To be honest with you, in your exam, I doubt they're going to get you to plot graphs and then get you to take several tangents and then take out lots of gradient readings and then replot a rate versus concentration, just because that's going to take too much time. They're more likely to give you some rate versus X graphs, perhaps ask you how to do it, and then ask you to identify the order of the reaction with respect to that. Jay, does that answer your question? Okay. Well, yeah, all right, Jay. So the initial rate, yes, that's exactly what you would do. So let me draw it here. Well, you got 2 ways actually of doing it. Remember, we're talking, just avoid getting confused between the 2 experiments. Here, to get the initial rate, you would draw a tangent at time 0, and you would measure the change in Y by the change in X. That's one way you can do it. The other way that you are able to measure the initial rate is to use the clock reactions. Okay, if you want to check out the clock reaction, what I'd suggest is probably the easiest thing, because I'm not going to go through the clock reaction now. You find a good description of the clock reaction here. If you go through to the year 2 section of our site, look in the required practicals 7 to 12 in this section here. If you're rattling through there, I think you'll find clock reactions are, here we are, initial rate method. Here you've got clock reactions around about 10 minutes in to the video there on initial rates methods, about 8 minutes. So that's where I'd suggest you're probably best off going just to check out the clock reactions. All right. Again, if you've got any questions that arise from that, do please just give me a shout. Okay. Final two things then we're going to talk about are the rate determining steps. No, it's getting late. And what we can learn from the rate equation. So importantly about the rate determining step. The rate determining step is simply the slowest step in a reaction. And the other thing about the rate determining step is that all reactants that occur in the rate up to and including the rate determining step, I'm just going to call that RDS, appear in the rate equation to the power of their stoichiometry. Now, just going to make that big, stoichiometry. What this means is, let's imagine we've got a scenario where, in fact, let's have a look down here. We've got rate here is saying KNO2. What that means is that NO2, there will be 2 reactant molecules of NO2 up to and including the rate determining step. And we'll look at that in a bit more detail just now. We're going to look specifically at this example for rate determining steps and why this shows us the importance of the rate determining step and what it can show us about the mechanism of some things. So again, I'm just going to make this big, seeing as I seem to have lost the zoom function today. Here we've got a reaction where we've got a tertiary haloalkane with the reaction of hydroxide. Now, this could be either a one-step reaction. This is actually called an SN1 reaction, but it could either occur in one step, where the hydroxide attacks and the bromide falls off, or it could occur in 2 steps. And that is where the bromide comes off from the carbon, like that, and the hydroxide then attaches to the positive carbocation. Now, if this reaction, so if it was hydroxide and then bromide falling off straight away, then the rate determining step, this would have to be the rate determining step, and the rate would be equal to the rate constant, the concentration of OH minus, and then CH3,3CBr, because there's only one step in the mechanism. However, if this step, that was the falling off of the bromide, was the fastest reaction, there would be no OH in the overall rate equation. And the rate would simply be proportional to the concentration of the haloalkane, like that. This is then something that we can actually experimentally measure. We can do some experiments, and what we find out is that the overall order of the reaction is first order. It is only dependent on the concentration of the tertiary haloalkane, and it is not dependent on the concentration of OH minus in the solution. What this shows and what it proves is that the nucleophilic substitution of a sodium hydroxide onto a tertiary bromoalkane here is a two-step mechanism, with the rate determining step being the loss of the bromide ion. And that's why these things are quite important. So let's have a look at a related question. Here we've got the reaction of NO2 and CO has a two-step mechanism. Overall, it's NO2 plus CO, but there's two steps to it. It says the rate equation for this reaction is rate. So, Jay, thanks. That's one of the reasons we do the rate equations, is you have to have the rate equation in order to be able to decipher this. So it's not something you can do without the rate equation. Okay. Here we see the rate equation for this reaction is KNO2 twice. What is the rate determining step? Well, there's two options. If it was step 1, then the rate would be equal to K, the power of NO2 twice. And if it was step 2, well, then the rate would be equal to K NO2 twice. Then it would also include the concentration of NO3 and the concentration of carbon monoxide. We're told experimentally that this is observed, and what this indicates is that step 1 must be the rate determining step. And that's because it's got the ratio of the reactants up to and including step 1 in the right quantities. We can also tell that this isn't a one-step mechanism, because in order for it to be a one-step mechanism, it would have to include the concentration of the NO2, because if it was one step, then the first step would have to be rate determining, and the rate equation would have to be NO2 and CO. So it can't be a one-step mechanism, and it must be a multi-step mechanism. Again, that's really important, because as an industrial chemist, it points out what you can actually do to improve the rate of a reaction. In this particular one here, where we got the rate is only proportional to NO2, there's no point adding any more carbon monoxide to get the reaction to go faster. Finally, then, the rate determining step for a reaction between reactants is 2A plus B. Predict the rate equation for this reaction. Okay, and so for this one here, we're assuming it's a one-step mechanism, so our rate would simply qualify to be A to the 2, concentration of B, and concentration of C. Again, we've got questions about those in the past paper question section. Right, time is getting on, and what I would like to do is just do a little bit of work on the Arrhenius equation. First of all, this is given to you. It's not something you need to remember. It's just something you need to be able to apply. What it does is it compares the rate constant in a reaction. You've got the activation energy. You've also got the temperature here. Importantly, that is in Kelvin. R is the gas constant. And A is the Arrhenius constant. Again, so the Arrhenius and the gas constant are both constants and are not things that will change. What you've got to be happy with is how you convert. Just be aware here that E is the inverse of the natural log. So if you want to change something, which you got e to the power of minus something, let's say e to the minus ea over rt, to get rt down on its own, you would take a natural log of that, and you would say that you would take the natural log okay. To get that down, you then take natural logs of everything, ln k, sorry, say ln k is equal to ln a, and then that just drops down to be minus ea over rt. So you've just got to be able to manipulate this equation and understand what it shows. You do not have to remember it. Okay. Importantly, what it does show is that as you let's look at the temperature first. If you increase the temperature here in this particular reaction, then you're going to, importantly, you're going to change the rate constant, and increasing the temperature will decrease this value overall, and in decreasing that value, because we've got a minus something to the log, that will actually cause the rate constant to increase. The other thing that we need to be aware of here, so increase the temperature, increase the temperature decreases minus E A over RT, and therefore what that's going to do overall is decrease the rate constant. Sorry about that. The other thing we need to be aware of here is if we, nope, I was right the first time. And I'll start again. And I'll start here, sorry, with the activation energy. The rate constant is telling us how fast the reaction will occur. So the rate constant is essentially how fast the reaction goes. So what's going to happen here is, as I make the value of this, the total value of this, as that gets smaller, so I'm going to do that over here. In fact, I'll do it down here. EA over RT. Let's get a different color pen. Oh, it's gone. E to the minus EA over RT. Because we got a negative exponential, if we decrease the size of the exponential, then K will also decrease. And if we increase the size of the exponential, K will increase. And so what we have to be aware of is what happens in these two examples. If we go rate constant as a function of the activation energy, if we decrease the activation energy, then minus EA over RT becomes a smaller, less negative number. And therefore, I'm going to run out of room here, so I'm going to go over here. And in fact, I'm just going to, and therefore, what that effect is going to do is the exponential becomes larger. And K increases. And if we think about that, that makes sense, because the rate constant, in other words, how fast the rate goes, is going to increase if we decrease the activation energy. It's got a lower barrier to get over. Let's have a look at what happens if we, the bit that I crossed out there, the rate constant as a function of temperature. Okay, so this one is, again, we've got to think about what effect we have on minus E over RT. So let's have a look. If we increase the temperature, what we're going to do then, this fraction is going to be less negative. Is less negative. And that's the confusing thing, it's because we've got the negative sign here. And therefore, exponential increases. That is this bit. And so K increases. And again, that in a qualitative argument makes sense on the basis that if you increase the temperature, well, you know that the rate of reaction increases. You've got questions about that? Because I know it's not the most obvious. Or does that argument make sense? Good. Okay. So what you just got to remember is that it's doing the opposite of perhaps what you think. Good. Okay, well, I'm pleased that helps. Remember, you don't have to remember it. You just got to be able to recall those. The final thing then that we'll look at this evening in the organic section is this picture here, which is, again, you might be asked to plot some data. And to do some manipulation of the Arrhenius equation. So the Arrhenius equation, K is equal to A, e to the minus EA over RT. We can rewrite that equation by taking natural logs minus EA over RT. Now, what I'm going to do is I'm going to say minus EA over R multiplied by 1 over T. Because what that allows me to do, and in fact, I'm going to rewrite that again, is equal to minus EA over R times by 1 over T plus the natural log of A. Because this, if you draw a straight line, mx plus c, m here is the gradient, c here is the intercept, x then can be plotted as 1 over t, and y can be plotted as the natural log of the rate constant, and this gives us a measure of the activation energy. And if we were to do just a gradient of this line, to do dy by dx, we could find out what the activation energy for a reaction would be, because the gradient here would be equal to minus the activation energy over R, and therefore we could work out the activation energy by multiplying by the gas constant. Okay, have we just lost connection again? Are you still there? I'm not sure if I lost connection there or not. Just drop me a message if you're still there. Okay, that sounded like a message to me, which is good news. Good, good. Sorry, it told me I needed to reconnect there for the chat room. Okay. Finally then, before we call it a night, just make sure that we're happy for rearranging K in our Arrhenius equation. Once again, you're given this equation, so not something to worry about, but we might be given things like values of K, and we might be expected to find temperatures. So make sure that you're happy with rearrangement. So here, the first step, natural log of K, natural log of A, minus EA over RT. Check that you're happy about rearranging both of these equations in order to get values for, well, anything in the equation, essentially. So you've got to be happy to rearrange here for T. So to get T on its own, the best thing that you're likely to do here is simply to add ln K plus EA over RT is equal to ln A. Then you can do EA, activation energy, over RT is equal to ln A minus the natural log of K. Because with natural logs, by the way, you just add and subtract them. And you should be able to here either give values for the activation energy, which can be equal to the natural log A minus natural log K multiplied by RT. Or equally, we might want to go in the other direction. We might want to get a value for the temperature, for example. And in that case, we might get here EA over RT is equal to the natural log of A minus the natural log of K. We would say that activation energy divided by the natural log of A minus the natural log of K times by R will give us a value for a given temperature. So just when you're working on these sorts of things, make sure that you're happy with rearrangements of that equation. Okay, I'm really sorry about the early interruptions. Like I say, they were out of my control today. I've had a slight issue with my machine, which is why we've not got the desktop. It should be up and running by next time, one way or another. I will make sure as well that all of the answers to the questions here that you might have, not a problem, guys. All of the answers to all of the past paper questions I will put online. I'll probably get round to doing it tomorrow now, but the questions are all here. Do have a go at so they've got bomb calorimetry. As you go down, they start getting more complex. You've got things like KC calculations. As you go through, you've got more things along the lines of the rate equation questions that we've been looking at later on. I will put on there tomorrow. I will put those into the webinar, past webinars. I will put the answers to all of those questions. You'll find those in the physical chemistry part 2. Check them out there. If you've got any questions, don't hesitate to talk or drop me an email, and we can always spend a bit of time going through some of those questions next week if you want. Otherwise, we will probably have a look at one of the specimen papers, probably the paper 2 specimen paper next week, and then start concentrating on the paper 1. I'll say goodnight there and look forward to seeing you on Monday. Don't forget, please share the site with your friends, and hopefully on Monday we won't have any technical issues as we start the webinar. Take care. I'll be around just for a couple of minutes, just updating with the answers to that page before we go. Good night, and I'll see you soon.